Hi, I'm Chamin, and I'm excited to present our work, Small Steps and Level Sets, Fitting Neural Surface Models with Point Guidance. This is a joint project with Itzik Ben-Shabbat, Dylan Campbell, and Stephen Gould. We propose a point-guided approach for surface reconstruction from point clouds, called PGSDF, that iteratively deforms the reconstructed surface until it interpolates the input points. We analyze why previous SDF-based methods often fail on difficult shape geometry and propose a metric to quantify this. We also analyze our method in the context of homotopy methods, giving insight into why it works well on difficult shapes. Neural SDF-based approaches optimize a neural network to represent the sign distance function, or SDF, of the underlying surface. The reconstructed surface is then the zero-level set of the optimized network. Here we show two examples of input points in black and their ground truth SDF function. To optimize for this, such methods use losses that specify properties of the true SDF. They also initialize the network to the SDF of a sphere to bias towards better solutions. This works well for target shapes with a similar geometry to a sphere. However, if the target geometry is quite different, neural SDF methods often fail. We explain that if the target shape's geometry does not align with the geometry of the current surface of reconstruction, neural SDF losses often will not guide towards the target SDF value. Based on this insight, we propose the Sion metric to measure the geometric alignment between a target surface S and a surrounding surface R. We define Sion as the percentage of self-intersecting outward normals on shape S, shown in red in the figure, where self-intersecting means the normal hits S before it hits R. If Sion is high, then the geometry of S and R are not aligned, so SDF losses are likely to fail to optimize R into S. If Sion is low, then optimization should be easy. Unlike standard neural SDF-based approaches, our proposed method does not directly optimize for a reconstruction of the input points. Rather, our method, called Point-Guided SDF or PGSDF, optimizes to reconstruct guiding points, shown in green. This guides our network to slowly deform the surface of reconstruction towards the input points. Thus, our method repeatedly alternates between moving the guiding points towards the input points and optimizing the network to reconstruct the newly moved guiding points. As the guiding points are moved a short distance each time, we avoid the issue of geometry alignment and SDF optimization is easy. Instead, the difficulty is in determining how to move the guiding points. Starting from a sphere, we use the guiding points to guide the surface of reconstruction to n exterior level sets of the target shape. Once we have reached the final level set, we then optimize directly on the input points. To get to one level set to the next, we take small steps and move the guiding points a small distance in their current inward normal direction. In particular, we move each guiding point towards the closest input point in its inward normal direction, shown for 3 guiding points here. After the points have moved, we optimize for reconstruction and then adjust both the guiding points and the network to be consistent with each other. We explain our method in the context of homotopy methods, which are a principled way to solve hard problems. Let m of theta be our hard problem. We define an easy problem, n of theta, and a way to deform n of theta into m of theta. By taking small steps along this path and solving the problem at each step given the previous solution, we can reach the solution to the hard problem. In our case, our easy problem is to reconstruct a high-level set, and our hard problem is to reconstruct the input points. We prove that our initial problem is easy to solve in the paper, and explain that each small step is easy as the relative Sion is small. Our results show that our method exhibits stable performance as shape complexity increases, unlike other methods. Our method's runtime is also adaptive, unlike most previous approaches. Finally, we show a visual comparison on 2 difficult shapes. Thank you.